Okay, so the perfect wall. So firstly, you're going to have to wait for about 20 slides till I show you the perfect wall, so you can't just see the slide number 2 and then walk out. And secondly, the perfect wall really isn't a wall as such. It's more an idea, a concept of how we should think about how we build walls, but also turn them horizontally, they become roofs. There's not that much difference there. All right. Okay, so building physics firstly, as hopefully many of us already understand, is the interaction between heat, air and moisture. If you mess with one, you mess with them all. And so in Australia over the last couple of decades, of course, we've been, let's say, increasingly good, but I'm not sure if good is really the word to use, but we've been increasingly focused on insulating our buildings. So we're trying to deal with the heat transfer across our buildings. We're somewhat less good at dealing with the air and moisture part. So you add insulation to your buildings, you're changing the way an air moves and critically the way in which moisture moves across that building. And as we all know in the building industry, it's moisture, it's water that scares the bejeevers out of us because that's the thing that kills our buildings. So the golden rules really are pretty simple, aren't they? Water kills buildings, that's fundamental. Water is everywhere, and so therefore we must clearly all be doomed. Well, yeah, we could all move to Mars and build buildings on Mars, and we'd alleviate the problem to a great extent, but we still wouldn't want to put people in those buildings, because we as people, of course, are generating moisture all the time from our perspiration, our showering, our cooking, and so on. And the rule of thumb seems to be, about sort of 10 kilograms of moisture, water, is being generated per day in a typical family home. So just think about that in terms of scale, 3 of those big milk cartons, that's a lot of water. So we've got to think about how we deal with that across our buildings. So water is everywhere, it is around us right now, particularly today, given how it's relatively humid out there. You can't get water out of our environment, and we wouldn't want to. If you think about a really dry environment, let me just take it back a step. If we look at these two pictures here, intuitively, if we said, well, which of these is wetter, we'd probably say the one on the left. That cold winter's morning when you've got that mist and fog lying low, you've got dew, possibly even frost on the ground. That's got to be a very wet atmosphere, right? As opposed to the one in the middle of summer where it's quite hot and it feels quite dry. And in a relative humidity sense, that is true, that it is very high relative humidity on that cold morning. But in an absolute humidity sense, it's quite different. So the holding capacity, the amount of water that's floating around invisibly in that really cold air on the left, on that cold winter's day, is actually about a third of that's floating around in the air on that warm day. And the benefit of something like relative humidity is to say it's the ratio, it's the proportion of water vapour in the air relative to the amount of water that could be held in that air at a given temperature. And so when you have very high relative humidity, you tend to get condensation. So hence the cold day, that cold air isn't able to hold all that moisture, and so it's appearing to us visibly as little water droplets floating around in the air, fog, mist, and it might condense on surfaces. So this is part of our problem, I think, is firstly we can't see that water vapour floating around us, but secondly that we sort of get a bit mixed up between it's cold, therefore it must be dry. Well, it actually might be quite the opposite. So while we are all doomed, we can shift the odds somewhat. We can try and play the probabilities. And I do hate phrases like we're going to build a building that has no chance of having any mould or condensation. We can't guarantee something. There is no zero risk. Every building has risks. Everything we do has a risk associated with it. But what we're trying to do is shift the odds, increase the chance that our building is going to survive for many decades, hopefully, or hundreds of years, without mould, condensation, rot, and so on. And so how do we do that? Well, there's probably two easy ways in which we can do it. Firstly, we need to stop water vapour from touching cold surfaces. And I'm going to use cold and condensing to mean the same thing here. So water vapour floating around in the air around us right now is fine, not a real problem for our buildings. It's only if that moves through to a cold surface that we have the risk of condensation. And secondly, we've got to assume the building's going to fail. Something's going to go wrong somewhere. And so have we designed this building in such a way that the rate of drying exceeds the rate of wetting? If we get an accumulation over time, over 24 hours, over a season, over multiple years of moisture in that building, then clearly we're heading for doom. So let's talk about the surfaces first. So how do we stop the water vapour from touching cold surfaces? Well, there's a few things we can do. We can minimise the amount of vapour that's generated in the first place. Okay, to some extent that will potentially help in a building. We can remove the vapour through something like dehumidification. We can heat the cold surface, and we'll come to that in a moment. We could try and stop the moisture, the vapour, from even reaching that cold or condensing surface. And then finally, we could try to make sure the cold surface is moisture tolerant. So in the case of the beer that we've just taken out of the fridge here, this scenario, you think, well, where's that moisture coming from? Clearly it's not wicking out of the bottle itself. So that moisture has come from the air all around us and is condensed on that surface. How do we stop that happening? Well, we could heat the bottle and it won't happen. The beer won't taste much good. We could stop the vapour from reaching the cold surface, put a stubby holder on it perhaps. We could make sure that in this case, it kind of doesn't matter that it's getting beads of water on it because it's glass, it's moisture tolerant. So avoiding the vapour, well, there's obvious things we can do, like don't hang your clothes out to dry inside unless you've got some other way of mitigating that moisture that's being added to the space. Gas cooktops are a bad thing whenever you burn methane, and that's what your natural gas is. You're getting an addition of water vapour into that space, setting aside all of the other indoor air quality issues with burning stuff inside buildings. Tropical fish tanks are off the agenda. You're keeping water at some 30-odd degrees, you're getting a lot of water vapour being evaporated there into the space. Cooking is a problem too. Should we stop cooking in buildings? Well, that's a bit of a hard call. But obviously those are things that are generating moisture. 30-minute showers, we should maybe put that on there too. So there's only so much you can do to avoid adding vapour into your building. Saunas, indoor pools, could have added all of those too. Like we've got a job at the moment where we've got a pool attached to the building and that frightens the bejeebers out of me. How are you going to deal with that really, in a way that you can have some assurity? We can remove the vapour, all the obvious things again. You have an extraction fan in the bathroom. The owner actually uses it, would be handy. Heat recovery ventilation, sort of mechanical ventilation that runs 24/7 in the building. Fantastic way of dealing with moisture loads in a building. Very fit and forget. It's not relying on the occupant to actually turn the damn thing on, because we humans are, of course, terribly fallible. An externally venting range hood to take the pasta generated steam out of the building. Dehumidification can help. But of course, we're not trying to eliminate the moisture. We cannot do that. You cannot get to zero relative humidity in a space. And you wouldn't want to, because as an occupant, we wouldn't last very long in that condition. And so coming back to that slide before where I was trying to show a really cold outdoor environment, think of those extremely cold situations you may have been in. Maybe you've been skiing somewhere, like in Scandinavia or, I don't know, the Rockies or somewhere, where it might be -10, -15 degrees. That's actually really dry air, because all of the moisture has condensed out of that air mass. And so you get the cracked lips and your skin feels funny and all of that sort of stuff. So we need relative humidity. And typically the range we talk about is somewhere between 40 and 60% relative humidity. So it's not possible to entirely remove the vapour. Heat the cold surface. So I'll sort of take a little convoluted route to this one. Firstly, you've got to think about where your cold surfaces are. So here's just a couple of situations outside. So this is one that kind of tricks us when we think about roofs, and I'm sure Dan will be talking to this as well, If you think of a clear winter's night, then you have visible to the sky, to space. And space is at absolute zero, which is like minus 273 degrees, super duper cold. And so there's nothing stopping radiation, radiant heat, from extracting heat from surfaces that are exposed to that night sky, and they get super cold. And so your roof sheet, you've just got standard, whatever steel roof sheet, exposed to that night sky, the surface, that's the temperature of that steel will go many degrees below the ambient temperature. So even if it's maybe 2 or 3 degrees overnight, which is not atypical in the middle of winter in Melbourne, the surface of that steel might be -5, -10 degrees. In much the same way that the windscreen on your car, when it's outside, will similarly get that cold. So it hasn't actually dropped below zero, but the windscreen surface has, and hence you get frost on the windscreen. Similarly, the grass will have dropped below zero and you get frost on the grass. Now, if that car was under a carport, the air temperature is the same as ambient, but the windscreen is not directly exposed to that minus 273 degrees, and so you won't get frost on that windscreen. Similarly, on the right there, well, just Googled and tried to find a random image, but you've got frost on the grass, but not under the tree. Why not under the tree? Because the grass under the tree is not directly exposed to that night sky radiation. So coming back to a wall, so here's our first wall finally. Here's a not atypical wall, I suppose. If we want to heat a cold surface, you firstly need to look at your build-up and think, well, where's my condensing surface in this assembly? So let's assume this is Melbourne, which is 80% of the year is a heating-dominated climate. So inside is warmer than outside. So the heat's travelling from right to left across this image. So the plasterboard is not our condensing surface because that's effectively at room temperature. Let's assume 20 degrees for argument's sake. As we move across the insulation though, the temperature is dropping. And so in this case, I've just drawn, let's assume a bracing board or something on the outside of our stud frame, a membrane of some description, and then I've got exterior insulation on that. And so the condensing surface here, the critical surface, is really that ply or OSB, whatever it is, that I've whacked onto the stud frame. So if I'm going to get condensation anywhere, it's going to be there. That's the cold spot in the construction. Now, if I don't have that exterior insulation on, the temperature of that ply, for argument's sake, is ambient temperature pretty much, outdoors, 4 degrees, 3 degrees, whatever it is. And that almost certainly is below the dew point, and so as moisture moves through that wall system, I'm likely to get condensation on the interior face of that ply. So how do I heat it? Well, I can't just run heating elements through it, that wouldn't be very sensible, but if I whack some insulation on the exterior face of that ply, I'm bringing the temperature of it up. Easy. So one of the other things we can do is we can try to stop the vapour reaching the cold surface. And I'll show you a wall again in a second. But just to digress for a moment back to roofs, which are really just walls, turned flat. If you think of your classic roof, like one in here, or sort of your carport roof that's just your steel roof sheet, then if you don't have something underneath that, in the winter you've got this air mass, this cold air mass with very limited ability to hold water vapour, moving in through, circulating, touching the underside of that roof sheet that, remember, is exposed to sky, night sky, so it is going to be very, very cold, and you'll get condensation and then that water drips off. And so what do we do in the carport? You put something like Anticon or one of those aluminium like air cell type products underneath. What are you doing? Are you heating the roof sheet? Well, no, the roof sheet is still exposed to exactly the same conditions that you were before. What you're doing is stopping the air from moving across that cold surface. Stop the air from getting to the cold surface. Then on the right here we have what a lot of us are doing nowadays, which is providing exterior ventilation out beyond the exterior membrane, our sarking layer on our buildings, on our roof in this case. But one of the consequences of doing that, by design, is you're encouraging airflow between the roof sheet and you're sarking. And so on that cold night, you've got this cold air mass moving up, carrying vapour with it, touching a cold surface, so you'll get condensation. And it'll drip down onto your membrane, and of course, hopefully you've put that membrane so it flushes it into the gutter, and so everything is fine. But you are, by design, getting quite a lot of water vapour, or condensing in that sort of assembly. Okay, so we need to stop the vapour reaching the cold surface in a wall. What's one of the other things we can do? Well, remember that the vapour drive, the direction that the water vapour wants to move, is from lots to less. It's like nature abhors a vacuum. We've all heard that phrase. If you have a high pressure system, that air is trying to move to low pressure. If you have a high temperature, the heat wants to move from high to cold temperatures. And in much the same way, if you've got a lot of absolute humidity, a lot of vapour inside your building, which invariably you do in winter, versus outside, then the vapour drive, the direction that vapour wants to move is from in to out. And so if I want to stop that vapour from touching the cold surface, the place to do that is towards the interior of my wall. And so here I've got this pink layer there, I've called an air and vapour control layer. It's trying to stop that water vapour moving out, getting cold as it moves across my insulation, and condensing somewhere in here, most likely on the back side of my sarking or OSB. So we need to digress to this air and vapour control issue. How is that vapour actually moving across that assembly? And it's doing it in one of two ways. The first and by far the most critical way is there's a mass of air. If I build an air leaky building, as most of our buildings are in Australia, very air leaky, and then that air mass, that 20-degree air that I've got sitting inside, perhaps 50% relative humidity, finds its way in through the wall, through the power point, across the skirting boards, wherever. There's cracks and leaks everywhere. It moves out through the wall, past the insulation, and it gets to a condensing surface, the sarking, and it condenses. So if you want to stop that movement of air, you've got to build an airtight internal layer to your building. The second way, though, is with diffusion. And this is a much trickier concept to understand. So the first one is the movement of air, convection. The second one is diffusion. It's molecular. And this nature abhors a vacuum type of thinking. Whereas if I've got a lot of water molecules floating around here, they want to go over here where there's far fewer molecules. Nature is trying to make everything into an equilibrium. And this is a far slower process. It does not involve the movement of air. And the way it's typically described is in a beaker, and you get a bit of dye and you put it in, and over time it just disperses out across that. Now, if you do that in your kitchen, what you're really getting is convection primarily, because you're getting small temperature gradients in that glass of water that's actually moving that around. But if, for argument's sake, you could go into a lab and you could set that beaker of water at a very constant temperature, then you will still see that dye disperse very gradually across that beaker of water through this process known as diffusion. So the key point here, though, is that the air movement by far and away dominates. And so if you're trying to stop the vapour from touching your cold surface, you've got to make sure you've got an airtight construction where that air barrier is on the warm side of the construction. It's too late if you put sarking on the outside of your wall and say, that's my airtight layer. So drying must exceed wetting. This is really about acknowledging that something is going to go wrong. All buildings leak at some point in their lives, so how do we ensure they dry? And this comes back to the sequencing, the way in which we actually put these buildings together, the layers together. So here's my AI-generated image, and gee, AI is intelligent, isn't it? Because you get like a water leak from there going into the bucket when you tell it to do like a bucket with holes and a tap. So anyway, what I'm trying to suggest here is it's about a game of rates. If you've got a tap feeding into a bucket with a hole in it, then you've got to make sure those holes are larger than the size of the tap, so that the drying, the holes, can ensure that the water doesn't continue to accumulate in that bucket. And so a building is kind of the same. We've got to make sure there's much more drying capacity in that wall than there is wetting capacity. So let's go through some walls and see if we can apply those principles as to how we actually should think about the construction assemblies, the sequences in which we put these walls together. So let's imagine that we've got our standard stick frame build, and let's put some weatherboards on the outside of it, direct to the frame, and let's decide now we're going to put some sarking on the outside of the frame. We did this pretty recently. Now that's kind of possibly okay, because I've got no insulation in there. So where's my cold surface? It's kind of the weatherboard's cold surface, but I'm heating through. I have this heat flux moving through this construction. When heat moves through, it helps to dry the assembly. Where things definitely go pear-shaped is when you do that and you insulate your wall as well as having that membrane on the outside. So now all of a sudden my condensing surface is the exterior of the frame, because I've put insulation in there, by design, to reduce the heat flow across that wall. So if I've got nothing here to stop the air movement and the vapour diffusion through that wall, then I'm going to have that vapour moving through. It's going to accumulate on the backside of my sarking, and let's say, I don't know, maybe it's made out of aluminium. I don't know why you do that, but maybe. Then you're going to get condensation, because that aluminium is pretty much the outside air temperature. It's a condensing surface. I've got very little other than the presence of my plasterboard to actually stop that movement of vapour across that wall. Another way to sort of try and think about this is, imagine if you're standing on the top of a hill in the middle of winter and you've got a jumper on, a nice big woolly jumper, and it's still. It's one of those beautiful winter days where it's super calm. If you've just got a jumper on, you're probably fine. It's nice and warm and you're comfortable. Now imagine that you're standing on top of that hill and it's also windy. It's 5 degrees and it's blowing a gale. The jumper is by no means adequate, because the air, the wind is just blowing straight through the jumper, getting to your skin, getting that evaporation, perspiration effect, which is making you feel freezing cold. So what do? You put on a Gore-Tex type of jacket. Very thin. There's no insulation benefit within the jacket itself, but it's protecting the insulation layer underneath. And a building is exactly the same. So what do? We get bulk insulation, like our jumper, and then we put a membrane around it to try and protect it from that wind washing. Now, if you put that jacket, go back to that jacket for a second, one of the characteristics of that Gore-Tex or those sort of fancy materials is that they can, and I didn't want to use this word, breathe. They're vapour permeable, vapour open. So as you stand there and you're perspiring off your skin, that vapour can travel out through that jacket. Now imagine instead if you wrapped yourself in aluminium foil or a bit of plastic or something. You'll be standing there, you won't be cold, but pretty soon your jumper is going to be full of sweat and you're going to be feeling pretty yuck. Well, it's exactly the same with the building. So, where does that leave us? This one is... Yeah, right. So here's the other thing then. So what we can do is, rather that sarking we had before, which may have been vapour impermeable, aluminium foil, we could say, well, let's replace it instead with something that's vapour permeable, something that can allow water vapour to diffuse across that membrane, that bit of plastic. And that's fine, except if I've whacked my cladding hard up against the frame, what have I really achieved? And dare I say, we kind of see this a lot with some of those, I can't remember some of the metal cladding systems when you look at them, that we're now calling up class 4 membranes, so vapour permeable membranes on the exterior frame, and then we're whacking metal cladding hard up against them. What's the point? you might as well just go for some cheapo sarking behind there, because it's not a vapor permeable construction. You've just whacked something vapor impermeable hard up against something that's vapor permeable. So if you want to make this sort of system work, you've got to ventilate the cavity. And so that's where we're at now. There's plenty of systems out there now that will say, put a vapor permeable class 4 membrane on the external surface of your frame, put a batten, create a ventilation cavity, have an opening, ideally bottom and top, that allows air to move across that surface, carrying away any moisture that should happen to move out through the wall. So we're improving the drying capacity of that system. Plus, we're providing a drainage plane, because we've got to assume when bulk water crashes into that cladding that some of it's going to get through. All claddings leak. And so when it does, have we got a drainage plane? But the drainage plane only needs to be 2 or 3 mil thick. Just tiny. It can be grooves in the back of an insulation board. But for the ventilation, you need a deeper cavity, because you're trying to allow sufficient air movement through to ensure adequate drying. So then we can go to the next step, and we can say, all right, so let's try and stop that vapor getting to that condensing surface in the first place, which is now my vapor open sarking on the exterior. How do we do that? Well, now we're at the double membrane sort of strategy, where we say, righto, we've got a vapor open membrane on the exterior, the blue surface here. We've got a vented cavity to the outside of that, so you put a vertical batten in to allow some air movement through, and then whack your cladding on, whatever it may be. It doesn't matter at that point. You've got your insulation in there, and then on the interior face of your wall, you're putting another membrane that's trying to help stop air movement primarily out through that construction. Now, what I've said there on this particular slide is an air barrier. So this is a vapor barrier membrane. So this could be, dare I say it, builder's plastic. Cheap as chips, right? And you do this in Scandinavia. They just get polyethylene, clear sheets of it, tape it together, stick it on the inside of the frame. And in that climate, it works, generally, although climate change is seeing to that. Because all you're doing in those super cold climates is all year round, you've got the vapor driving from in to out. So as long as you can stop the air movement moving into your wall, and you can stop the vapor diffusion, which polyethylene will do perfectly well, then that will be fine. But it's a bit trickier in our sort of climate, because in the summer everything's reversed. And particularly as we do now with air-conditioned buildings, we might be trying to cool this indoor space to 25 degrees when it's north of 35 outside. And so now the vapor is actually trying to drive towards the interior. And there's very little stopping the vapor from doing that, because I've got a vapor open membrane here, so it's allowing vapor diffusion inwards. And so the risk now is that I'm going to get condensation on the exterior face of that polyethylene, because it's a vapor barrier. It's cold, so my condensing surface now is the internal membrane, as opposed to the external surfaces that it was before. So using a vapor barrier is probably not a great idea in our climate. Maybe Mount Buller it'd be okay, certainly not in Melbourne. And so instead, we go with one of these, air and vapor control membranes, intelligent membranes, variable vapor diffusion. They've got a whole bunch of names. But essentially what they're doing in the winter is they're staying vapor closed, or as a vapor retarder. They're precluding the movement of vapor diffusing across that membrane, plus they're taped and sealed, so they're preventing the air movement. Tick. Then in the summer, if they need to, and they only do this at higher relative humidities, if the humidity builds up on the exterior face of that membrane, they sort of open is not quite the word, but what they're doing really then is allowing that vapor to drive back towards the interior. So you're not trying to trap it on that condensing surface. And so that's a really excellent wall assembly. So we're close, but it's not perfect. it's kind of not quite perfect because so a few things come up. So firstly, there's mice and all sorts of questions about resilience of these sorts of assemblies, I suppose. But secondly, the problem is the climate. So in Melbourne, it's pretty definitive. That's the sequence you do things. You do your air and vapour control layer towards the interior, you do your vapour open membrane towards the exterior, because we're a heating-dominated climate. But what if we go to Sydney? What if we go north to Byron and then to Brisbane and then all the way to Cairns? Well, things change, because it's a bit like what we were showing before, where the vapour drive now is from the out to in. And we can't go into our wall seasonally and flip the membranes around. So it becomes a much more difficult problem to work out, well, at what point north do things shift? And more to the point, as the climate changes, we're going to see higher temperatures, higher relative humidities, higher absolute humidities. And so that point, so say for argument's sake, we drew an arbitrary line and say, anywhere south of Byron or something, we're going to need this sort of assembly, and north of that, we need to flip it around. But that's going to change over time, and we can't go back and retrofit our buildings as that line moves south. So here's another version that we can do. So in this case, we're going to try and separate all of our control layers of our building out. So what we've got here is our structural layer, our stud frame, no insulation in it. And then with a plier or an OSB, maybe we're going to use a peel and stick type of membrane. That's our air and vapour control layer. And then on the outside of that, we have our insulation, and then we have our batten, and we have our ventilation and drainage. So that is pretty much the perfect wall. So why is it the perfect wall? Because in the winter, my structure, all my moisture-sensitive materials are warm. And warm materials are dry materials, usually. So we're keeping our sensitive materials dry. Our membrane here is going to serve a great function, because if I've got air moving out through this construction, this surface is warm and therefore not going to have condensation on it. And then from the outside, if water drives in past the cladding, which it must, and this insulation is not moisture sensitive, so you're not putting glass wool there, putting something like a mineral wool, like a rock wool, maybe, dare I say it, even a foam, like an XPS, a PIR, whatever you want, then any water that gets in behind that can drain away. So you just have a millimetre or two just to allow that water to drain away from that system. But you've got, coming back to what we were saying earlier, you've got a moisture-tolerant design, because water vapour can't get to any of our moisture-sensitive surfaces, and we're allowing drying. So this really just sort of reiterates that. You think about the functional layers that you've got in that building. The cladding is there to reflect away 99% of the water. Almost all of it, this rain now, bounces off the roof and it's gone. But you've got to assume that some gets through. So you have a cavity there that allows drainage out. You have ventilation just to make sure it can dry out, it can evaporate out. You've got continuous insulation with the exterior insulation. So no longer are we mucking around trying to put insulation between our structural layer. And then we've got our air, water and vapour control layer all in one. So we've just come back down to one membrane system on this face here that's on the warm side of my construction. And then in the summer, if I get vapour moving through, the idea is even if I get condensation here, let me see. Yep, so I've just said that bit. In the summer, the vapour drive is towards the interior, but what we're trying to do is keep that vapour away from our moisture-sensitive materials. So it's going to condense against our membrane, which is moisture-tolerant, drains down, and whatever insulation you've got here, and my fave right now is something like a rock wool, a mineral wool type product, then it just comes with these little grooves on the back face of it. So when you put it up against the frame, any water droplets that form can just drip down and away. And so that design should work, in theory, in any climate. So fire and forget, off you go. You don't have to worry about it anymore. Okay, so just to finish up, water is everywhere. We are doomed. You've got to keep water from the cold surfaces. So if you've got some unusual wall system that the architect has come up with and you're looking at it, think, well, what is my condensing surface, both in winter and in summer? And am I stopping the vapour from getting to that? Assume the building is going to get wet, so make sure you've got drying in there. And this is where it gets really tricky with some of the foam-based products, because they are vapour retarders. And think of your hierarchy of controls. Any risk mitigation strategy says, what's my number one risk? Well, it's always bulk water. It's the rain. If you've got a rain leak, nothing else matters. So deal with that first, get your flashings right. Then it's about air control. So stop the air moving across your assembly. Then it's vapour diffusion. But very few, if any, buildings have ever died as a result of vapour diffusion alone. It's always air. And then finally, you've got to get the thermal control, of course. But we sort of have forgotten about the first three and we just deal with thermal control typically. And then finally, I just whacked that down there this morning. I don't know if anyone's seen this. Building Science Corp, as many in this audience probably know, is a really cool website with hundreds of free resources out of the US on building science. They've just got this really cool AI assistant that's actually pretty bloody good. And unlike most of your ChatGPT that's just like scouring their whole internet, so coming up with any old crud, this one's only based on the Building Science Corp website, so you have some reasonable assurity that it's actually pretty decent information you're getting. You can just go on there and whack in your building science question and you get a pretty coherent response. So there you go.